Welcome back. Let's explore the rationalizing technique of evaluating limits. Let's take a look at this sample. We want to find the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. First, we have to begin by direct substitution to determine that the indeterminate form becomes 0 over 0. So by substituting 0 in for x, we do indeed see we get our indeterminate form of 0 over 0. Now we're going to rewrite the fraction by rationalizing the numerator. In the past, we've rationalized the denominator. We use our difference of squares pattern, our a squared minus b squared. So we've got the square root of x plus 1 minus 1. So we multiply the numerator and denominator by the square root of x plus 1 plus 1. And we do that both top and bottom, or to the numerator and denominator, because we want to just multiply by 1, and we don't want to change our location on the number line. So following our pattern, the square root of x plus 1 quantity squared just becomes x plus 1, and then 1 squared is 1. So we end up with x plus 1 minus 1 in our numerator. And let's just leave our denominator as is, x times the quantity x plus 1, the square root of x plus 1 plus 1. A little simplifying, our x's cancel here, so we divide out our common factor, and we do indeed get all the way down to 1 over the square root of x plus 1 plus 1. Now we can go ahead and evaluate by direct substitution. So we substitute our 0 in for x, and we get 1 over 1 plus 1, which is 1/2. So the limit of our original function, the square root of x plus 1 minus 1 all over x, as x approaches 0, is 1/2. And you can check this graphically on your graphing calculator. As you can see here, when you input this into your graphing calculator, we're going to use the original function. As you can see, our x values begin at -1, because in our original function, we don't want negative square roots. We want real solutions here. Our domain is constrained from all real numbers greater than -1, but we also cannot have a denominator of 0, so we're undefined at 0, and it appears that the limit as we approach 0 of this function is the y value of 1/2. And we'll get some more practice with this when I see you in class.